This is a video for final project Dynamics Miami University MME 311, and I am going to talk about Coriolis acceleration in this video. The textbook definition of Coriolis acceleration says that it is the acceleration due to rotation of the Earth experienced by water particles moving along the Earth's surface. This definition means nothing to us in a dynamic sense point. So let's take an example. For example, here is a merry-go-round. Here's person A, B, C, and D. And person A has a ball. This merry-go-round is stationary as of now, and person A is able to throw the ball directly to D or C or B without any problems. But once this merry-go-round starts rotating in this manner, doesn't matter which manner, but we're going to take clockwise for now, person A will not be able to throw the ball directly through C. So if it's rotating, after like a split second, A is going to be here, D is going to be here, C is going to be here, and B is going to be here. But if person A throws the ball here, if it's traveling in a straight line, going to be traveling in a straight line, and we find out that soon person D receives the ball instead of person C. To an observer above, it will look like a straight line, but it actually deflects. Looking at it a little more deeper, there's another example. So let's say there is this rigid support here and has a bar fixed to it, which is free to rotate in this theta direction. It is frictionless, first of all, and has some ball bearing or a slider attached to it, which it's freely to move about here, which will give some velocity. And here is E theta, and here is ER. There's no acceleration in the radial direction. Let's draw a free body diagram of this, which would be something like this. That's the normal force. If you look at the acceleration equation, everything's going to zero out, because there is no radial velocity. So your first and your second terms are going to cancel out. And if you just look at an equation of F equals ma, your normal force just remains as m, and a is just your 2 times r dot theta double dot, sorry, and e theta. That e hat, that becomes your equation for the normal force. Looking at the same example for this bar, if we look at this initial bar path, let's say this is the bar initially. Same thing, ER and E theta. Let's say here is the slider or the ball bearing, and the force is acting in this direction. If the force is acting in this direction, your acceleration is also going to act in this direction. Let's say after a second, there is some movement in the bar, just as I showed in this half, the theta direction, and this starts moving here. So this changes, and so does this. We'll call this E of R1, and we'll call this E of theta 1. And you'll still see a good part of the acceleration is still in the E theta direction, and there is just a tiny bit of acceleration in the radial direction. So the acceleration, there still is some acceleration in the radial section, which contradicts this part. So let me just write down r dot dot is not equal to 0. So that just means that E theta result of that is just change in the radial distance. And acceleration in the theta direction causes some second derivative of radial distance. So if you look at ER, this is just r dot dot minus r theta dot squared. This goes to 0, and this is ER as well. But since r dot dot is not equal to 0, your r double dot becomes equal to r theta squared, which is also your centripetal acceleration. And you find out that this entire equation just goes to 0, but its components are not 0, because there is some acceleration in the radial direction from the derivative of the radial distance. Also, if we look at it from a from an energy perspective, we have this equation, which is E equals half I omega squared. This is always increasing, because there is always some work in to maintain constant omega. And since omega is constant, only polar moment of inertia is changing. So like this can just go to zero. And if we go back to the same diagram again here, for energy perspective, moment of inertia is going to be super small here. It's going to be a little bigger, and it's going to be the largest at this point. If we look quantitatively, we can always identify polar moment of inertia based on acceleration radius, which is also equal to the change in kinetic energy or work in